Okay, hi everybody.
Hello.
Happy Thursday. The game plan today is to keep going through chapter 27. We'll see how we do with the lecture today. This is actually a fairly short chapter, and chapter 28 that we're going to cover next week really gets into a lot of the details of more complicated circuits. So it's possible that we're going to finish the material that I have planned for this week today. And if we do that, we might just cancel tomorrow's lecture. So we'll see if we can get through everything today and leave your Friday a little bit more open than usual. Okay, let's go ahead and jump in then and get started. Let me share my slides. Okay. So yesterday we introduced and tried to motivate the idea of an electrical current. So we did some demonstrations to try to show you or give you the feeling that the idea is that we're really in a different, right? We're dealing with charged particles moving in an electric field. They're flowing in this material. It gives them this current, right? We can measure the electrical current, how much charge per time flows past a particular area in, say, a circuit or any region in space where we have charged particles moving. And that's really a different situation than these electrostatic problems that we have been doing up to now, because there's dynamics associated with it. So for instance, we saw that the wires that are a continuous piece of conductor are no longer assumed to be at a common potential, but there has to be a potential difference that's driving those particles through the material. Okay. So we're going to carry on with these ideas today. Let me get the chat window open here. Okay, so the new concepts that we're going to introduce today are, first of all, the idea of conductivity and resistivity. Okay. So here's the idea. Remember, we introduced yesterday this idea of a current density. This thing J was equal to the amount of current per unit area that flows through some material, right? So if I had some material and it has some cross-sectional area A and there's some current I flowing through it, I can calculate that current density. And what we can imagine then is think about a material, different kinds of materials, and we establish some electric field in that material that's going to drive the charged particles through the material. And different kinds of materials might have a different response. So maybe I have a piece of copper, or maybe I have a piece of aluminum, and I put the same electric field across, right, inside of that, set up the same electric field, right, have the same, what would I do to set up the same electric field? Well, I would have the same potential difference over the same length in that wire. So I set up the same potential difference across that material for the same length. It creates the same electric field. And then we can ask, well, what's the current density, right? So I might get a current density for the aluminum, and I might get the current density for the copper. And what I might see is that for the different types of materials, even though they have the same potential across them, I'll get different current coming out of the system. So it's sort of it can be related to several different factors, right? We saw from the current that it's related to the electron density and sort of the force that gets moving on things, and sort of how tightly packed those different nuclear points are inside of the material that the electrons are bouncing through. So there's some complicated, right, differences of the material structure related to all those different factors, but we can kind of sum all that up into one physical constant that we call conductivity. And so this is a factor. You can see it has all those different factors sort of wrapped up into it, but it's just a property that we can measure of some material that tells us, for a given electric field set up inside of that material, what is the current density that it's going to produce. And so the current density, the conductivity, it has units like ohms. We're going to come back to ohms in a second. That's going to be our standard unit of resistance. Inverse ohms per meter. Inverse ohms per meter are the units that we have on this guy. We can also talk about the resistivity, right? This is just the inverse of the conductivity. Okay. So what does this number say? This number says, imagine I have fixed electric field. The higher the conductivity, the stronger the current density that will be produced. Right? So materials that have a high conductivity will produce a lot of current per cross-sectional area for an applied electric field. Currents that have a low conductivity will produce very little current with an applied electric field. Okay, and the resistivity just is the inverse of that quantity. So high resistivities mean low conductivities and means for a fixed electric field or a fixed potential across some portion of that conductor, I get low current response. Okay. You can see here's a list of resistivities and conductivities for some standard materials. So the things that we think about being good conductors like aluminum and copper and gold, the reason we like to use those in electrical circuits is because of their high conductivity. You can see their conductivity is something like a few 10 to the 7th inverse ohms per meter, inverse ohm meters. Okay. Whereas if you look at something like carbon, it's or tungsten or nichrome, things that are poor conductors but still let current flow through them, you can see that they're orders of magnitude several thousand times lower in the conductivity, and so they don't like to push as much current through them for a given set of materials. Okay, so that's the idea behind resistivity. And then the last bit that we want to focus on today is the relationship between the electrical current and the potential difference that gets set up across that piece of material, right? So if I imagine that I have, a piece of conductor or a wire, and I have some voltage difference across that wire, we want to know how much current is going to drive through that thing. Well, the amount of current, right, we just said that the current density is equal to the conductivity times the applied electric field, something like this. Okay. So if I want to get the current, I know the current flowing through this thing is going to be like J times A times the area. That's equal to the current flowing through that thing. And so that should be equal to the conductivity times the electric field times the area, okay, something like this. And right, this has a few bits to it. So look, there's a unit here that's like E, and then area. What is area? Area is like square meters, right? Well, I can change that to a voltage. Remember, a voltage is like the electric field E times D, right? Gives me a voltage. The electric field applied across some distance gives me a voltage. So I can see the E and one of these, E times a length here, right? If I take E times L, that's going to be like the voltage of this thing, the delta V across this guy. And if I take A and I divide that by L, I end up with something that's going to be, and I have this thing that's like this. If I take the inverse of that thing, there's a collection of physical constants that I have here, and those are related to this quantity that we call the resistance of the wire. The resistance is just the resistivity that we described before. So low resistivity means a lot of current will flow for an applied electric field. And then since that was, the resistivity was sort of per unit volume, right? I multiply by a length and divide by an area to get the resistance applied by that object. You can try to think about this right in terms of water flow. Remember, we said that electrons that are flowing in copper wires act a lot like incompressible fluids, like water flowing through pipes. And so you could imagine different materials that you stuffed into the pipe, right, would have, like if I suddenly inside of my pipe put a section of sponge, right, jammed a sponge in there, the water would flow, but it would suddenly flow very slowly because that material would have a low resistivity. And the amount of total resistance would depend on how much of the pipe that I filled with the sponge, right, the cross-sectional area, if I only put the sponge up halfway across the cross-section of the pipe, and how deep I applied that material. So you can sort of imagine, right, the longer that blockade, the more low resistance I have, or the more high resistance material I have in my material, the larger the resistance. And what does that do? That leads to this relationship that's called Ohm's law. Okay, we're going to come back to this over and over again. It says that the current is the ratio of the voltage difference divided by this property that we call the resistance, right? That depends on the geometry of a piece of material that the electrons are trying to flow through, multiplied by this resistivity term. I can also turn this around and say delta V, the potential difference, is equal to IR. So if I can measure the current flowing through something and I know the resistance, I can tell you what the potential difference is across that object. Okay. So we're going to play with these ideas as we wrap up the slides in this chapter, and we're going to play with Ohm's law extensively in the next chapter. Okay, so let's try some problem solving. So this one is going back to yesterday. I have a junction with 4 conductors that lead into the junction. And I see that there's current flowing into the junction along 2 of the arms of the conductor. One has 2 amps and one has 5 amps. And there's current flowing out of that junction of 9 amps through one arm. Can we find what's the current flowing through this 4th arm of this conductor? Let's turn on the polling and see what you guys think. Okay, I'm going to go ahead and stop the poll. So the popular answer was 2 amps to the left or into the junction. Well, what are we going to do here? We're going to use that junction rule that we saw yesterday, that the sum of all the currents flowing into the junction had to equal the sum of the currents flowing out of the junction, right? This is a statement of current conservation. If I have some number of electrons per second flowing into this junction, the same number I have to leave, otherwise I would get an accumulation or depletion of electrons at that particular position. So let's see, I can see that I have 7 amps total current flowing into the junction. I have 9 amps flowing out, so that means I need an additional 2 amps flowing into this thing, right? That would give me a total of 7 plus 2 plus 2. For the current flowing into the junction, 9 amps flowing out. Those two are equal to one another, so I can see that it has to be 2 amps to the left here. What about this one? I have 2 wire segments. So this is a funny shaped piece of conductor. Okay. It has a smaller, right, conductor segment 1 has a smaller diameter than conductor segment 2. They're made out of the same metals, same materials. And what I've measured is that there's current that we're going to call I1 that flows into that narrower segment number 1. How does the current that's flowing in I1 compared to the current that's flowing in segment 2? So there's some current I2 that should be flowing in here. How do those two compare? What do you guys think? Okay, I'm gonna go ahead and end the poll. So a lot of you said B, but there was some split between A and C. Well, let's think about this. Remember, we're thinking about the electrons like an incompressible fluid. So we're thinking about these like mediums that are completely full of electrons. And then I'm going to push a certain number of electrons in here in a given amount of time, right? That's the current. If I push that number of electrons in here, because this is completely full, it's got to push the same number of electrons out here into segment 2. And those same number, right, some number of electrons enter here. The same number have to flow across this boundary, and the same number have to flow across this boundary. So the current is conserved, right? This is just like a funny shaped boundary. The current has to be constant through this uniform conductor. There's only one path here for the electrons to flow, and so there has to be a continuity of current across this object, right? I think again about what would happen with some pipes filled with water. If these were completely packed with water and I pushed a gallon of water in the left-hand side, I would have to have a gallon of water come out the right-hand side. So I would have to have this conservation of current or flow through this system. So the answer here is that the currents, the electrical currents are the same. Same problem. What about the current densities? What about the current density? Remember, current density is my current per unit area. How does the current density compare here? I'll give you guys 5 more seconds. Okay. So almost unanimous that we think current density in 1 is higher. Well, we just established that I1 equals I2. We can see that the area of 1 is less than the area of 2, and so therefore J1 has to be larger than J2. So the current is conserved. The thing that's different here is the current density. What else would be different about these two? Well, we just established this relationship that says the current density is equal to the conductivity times the electric field. Right? How do the conductivities compare between segment 1 and 2? Well, it's the same material, the same metal. Conductivity is just a material property. It only depends on the type of material. So conductivity 1 has got to be equal to conductivity 2 if they're the same materials. You just go to the table and look up the conductivity values for, say this is copper, for copper. So if J1 is larger than J2 and conductivity 1 is equal than conductivity 2, that relationship there says that we can infer that the electric field in segment 1 is greater than the electric field in segment 2. It's going to have more current density. It's going to have a stronger electric field, but the total current is going to be the same. Current is conserved, right? Current doesn't have an area term in it. The current is just conserved as I move through an object, right? The current densities can vary, but I have to have a conservation of particles passing through some position in a given unit of time, so that the total electric current has to be conserved as I move through some position, right? The sum of the input current has to equal the sum of the output current. I see Devin has a question about if current is independent of the area. Devin, did I already answer your question with some of the discussion here? Perfect, thank you. Okay. So the electric field for 1 is greater than the electric field for 2. We just saw that. So let's think about this. Here we have 2 wires, again, made out of the same material. Okay. Wire 2 now has twice the radius as wire 1. So I can see this relationship. And the electric field is 1/3 the strength. Okay. The electric field is 1/3 the strength. Let's see if we can compare some of these quantities. Well, which one is going to be easier to compare here? I want to compare the currents and I want to compare the current densities. Let's start with the current density. Why do I want to start with the current density? Because I know the definition of the current density is just the conductivity times the electric field. It just depends on a material property, something I can go to a lookup table, look that up for whatever material my wires are made up of, and the electric field. And that's great because I was given information about that in this problem. So let's have you guys in the poll answer which of these relationships hold. In this particular problem, which one has the higher current density? Okay, I'm gonna go ahead and end the poll in about 5 seconds. Okay. So almost all of you selected A, that current density 1 is greater than current density 2. Well, we can calculate that. Let's just do the calculation. J1 is going to be equal to conductivity 1 times electric field 1. J2 is going to equal to conductivity 2, but these two guys, right, are the same material. So that means conductivity 1 has to be equal to conductivity 2. They're the same materials. So this is also, it has the same conductivity, but the electric field is E1 over 3. So I could take the ratio J2 to J1, okay, and this is just going to give me this is just going to give me 1/3. So J1 is larger than J2 by a factor of 3. What about this guy? What about the currents? Can we figure that one out? How about the total electric current flowing through each one? Okay, I'm going to go ahead and end the poll. Many of you selected B, but some of all choices were selected. So let's work through this. Well, we just established that J1 is equal to 3 times J2, right? The current density for J1 is higher. What's the definition of current? Our current, I1, has got to be J1 times that cross-sectional area. That's how cross-sectional area 1. That's how I get to a current, right? It's the current density times the area. I2 is going to equal J2 times A2. Well, what's the cross-sectional area here? J1, A1 is going to be pi R1 squared, something like this. What about this? Well, J2 we just established is equal to J1 over 3, a third of J1. But now the diameter is twice as large here. So this thing is going to be like 4 times pi R1 squared. Right, I get a factor of 4 coming out because I have twice, right? This guy here is like, right, this whole thing here is like R times twice R1 squared, and I can pull the factor of 4 out. So now I can see that I have common factors of J1, pi, and R1 squared here. So I can see that I2 has to be greater than I1. I2 equals 4/3 I1. I can come up with the exact ratio. Okay, is that clear? So hopefully this is getting to the difference between current and current density. And we're playing around a little bit with the idea of conductivity here, right? That the conductivity is related to the is related to the current density. It's just scaling the electric field. Okay, what about this one? Now we have 2 wires, so 2 pieces of conductor, and the length of wire 2 is twice the length and twice the diameter of wire 1. What's the ratio of their resistances here? So diameter, right, this is D1, this is D2, this is L2, and this is L1. And I know that L2 is equal to twice L1, and I know that D2 is equal to twice D1. Oops. Okay. How do their resistances compare? Let me relaunch the poll and see what you think. Remember our definition of resistance. What is it? It's the resistivity times the length divided by the area. Okay. Let's go ahead and end the poll. How does the resistivity compare between these 2 segments of wire? Well, if we assume they're the same material, then resistivity 1 has to equal resistivity 2. Again, it's just a material property, so you go look that up for copper. If you have the same material, you have the same resistivity. So the only thing that's different here is the geometry of this setup. So the numerator for resistor 2, I have twice the length. But for the area, I've got twice the diameter. And remember, when I'm taking the area, I'm going to square the radius or square the diameter term. So I'm going to I have 4 times the area. Right? So A2 is equal to 4A1. And we already know that L2 is equal to twice L1. So the resistivity of object 2 is lower, right? By how much? By a factor of a half. Oops. Sorry, I see Devin has another question in the chat. Devin, Devin, can you yeah, we can go back to that. You have a question. It says, you said that you're looking at the equation that says that I is equal to E. What is the next part there? IE, is that supposed to be the electron current, or?
Yeah, the electron current.
And what is E in that expression?
The electric field.
Where are you finding that that equation?
I think it was on the lecture videos.
On the lecture video?
Yeah.
So the current, remember the current should be, so how is the current related to the electron current? It's not times the electric field. What goes here? Does anybody remember what goes here to convert an electron current to a current? It's got to be the charge of the electron, right? It's little e that goes here, not big E. So I think maybe that's where you're getting confused, Evan. This is the electron charge.
Okay, yeah, I just read the wrong.
Because this has to be, remember, this thing has units like number of particles per second, something like that, right?
Right.
And so this has to be charge units because we need to get something that when I multiply some number of, right, some fundamental charge by the number of electrons, that gives me like the total charge. So this has to be charge times number of particles, and then that gives me the total charge per second, and that gives me the current.
Okay, all right, thank you.
Okay, yep, good question. Okay. Let's keep going. So now let's come to Ohm's law here. Ohm's law. So here we have a piece of conductor, and we see that there's some potential difference across this piece of conductor, and it's producing some current flowing through it. Okay. This says, can we determine what the resistance of the wire is? What is R? So let's have you guys calculate R here. So they're showing you in a graph what the potential, as the potential difference changes, what the response current is. So what's the relationship we need to hear? We need to use Ohm's law. Delta V equals IR. Okay, I'll go ahead and end the poll. Right. So notice what Ohm's law says here. It says if I want the resistance, it's going to be the relationship of delta V to the current. It's a linear relationship here. So at any of these points, right, I can just go to that position and I can find delta V, that's 0.5, and divide it by the current, 25, and I should get the resistance. And over here, we'll find that the delta V was 1 volt, and the amps flowing through it were 50 amps, something like that. And you can see that I get the exact same ratio. I still get that same resistance here. Okay. So the resistance is telling me, right, the resistance is a physical property of the piece of conductor. Right? Remember, resistance is just like resistivity times the length divided by the cross-sectional area. Right? This is just what, right? This is basically only depends on what's the material, right? That's encoded in the resistivity, right? How long the material is and what its cross-sectional area is. So the resistance is totally determined by the shape of the conductor that the current is flowing through and the material that it's made out of. The delta V is a choice, right? I can establish a different potential differences across it, right? I could hook it to different external voltage sources, different sized batteries, for instance. And the response or the resulting current flow, right, is the relationship between those two things. And so I get the same resistance, right? If I put different voltages across this same conductor, I get different currents out, but I always get that same resistance coming out of this thing. Okay. What are the units of resistance? Well, it's volts per amp, okay? And this is what we typically call an ohm. So ohms are the standard units that we're going to talk about for resistance, and it's just volts per amp. All right. So I can see here that the answer has to be B in this case. So we can also answer questions like this, right? Again, this is just an application of Ohm's law. This says if I measure the current, I see I have 15 milliamps of current connected across the terminals of a 9-volt battery. What would the resistor have to be? What would the resistance be? Well, now I can just use that. I know that V is equal to delta V is equal to IR. I want to find that resistance. I know R has to be delta V over I. They gave me all these things. This is just going to be 9 volts divided by 15 times 10 to the minus 3 amps. And I can calculate a resistance. It's a very simple relationship. It just says there's a linear relationship between the current and the voltage, and that scaling factor is what we call the resistance of that material that the current's flowing through. So that's essentially all the material that's in chapter 27. And so I just wanted to walk through the sequence, right? And so what we've tried to establish here is sort of the cause and effect sequence that leads to current flowing in some material. Okay. Let's just walk through this just to recap what we've seen here. We need, in order to get a current flowing, we need some sort of potential difference. We need a delta V. Could be a battery, could be a capacitor, right? Very frequently, we could plug it into a wall that gets its potential difference from somewhere else. But we need a potential difference somewhere. Why? Because we need to be able to have a variation in potential, because we know that variations in potential, right, dV dx, variations in potential lead to electric fields, and I'm going to need an electric field to push charged particles through the wire to generate a current. So the first thing is I need a potential source. Okay. Right? A battery, remember we saw yesterday, a battery is a source of constant potential. Is a battery a source of constant current? Does a battery, if I have a circuit, does a battery always provide the same current? What do people think? Aaron says no. What do other people think?
An ideal battery?
Yeah, an ideal battery. Is it a source of constant current? Sorry, hold on, let me turn my volume up. Go ahead, can you repeat?
Wouldn't it depend on the circuit?
Yeah, so that's telling you, right? That's correct. It would depend on the circuit. So therefore a battery is not a source of constant voltage, right? A battery, say it's a 3-volt ideal battery. If I hook it up to a resistor that's going to have, say, 3 ohms, or I take that same battery and I hook it up to a resistor that has 6 ohms or 1 ohm, whatever we want to say, 6 ohms, some different resistance. The battery always provides the same voltage, right? It's going to provide 3 volts across that resistor, but the current is going to be different, right? In this case, I'm going to have what we know that V is equal to IR. So we know that the current is equal to the ratio of that potential difference across the resistor. So I'm going to have 1 amp of current flowing through this thing, okay? And I'm going to have a 1/2 amp of current flowing through this one. The battery is just going to provide the current that is associated with the resistance that's available in the circuit, or that's throughout the circuit. So this is a point of confusion for some students, that batteries, especially ideal batteries, we're thinking about them like sources of constant potential difference or constant voltage, not constant current sources. So then the second step is, once we have that potential difference from the battery, we can connect it to some wires, right? And that battery delivers that potential difference, right, across those wires or through those wires. The delta V of the wires has to match the delta V of the batteries. Why? Because I just have common conductors here. By the time I make my way around this loop, right, I've got to be back, right? I have to go through that wire and I have to have the same voltage drop around that wire. And because there's a voltage difference through that wire, it's creating this electric field. Okay. The electric field is just like the strength of that electric field, right? Once I have a connection across the thing, has to just be like the potential difference through the wires divided by the length of wire in the circuit, something like this. Once I have an electric field, then that electric field starts pushing the charged particles around, right? Creates a current density. If I multiply that by the cross-sectional area, I get current flow. And the amount of current that I get depends on that supplied voltage, but also some properties of the material and the geometry of the situation that I have set up here. Okay. We have Ohm's law here. So that's kind of the sequence of events, right? That chain of events is really what I want you guys to take away from this chapter. We have a potential source. The potential source shares that potential difference through the conducting wires, generating an electric field. The electric field pushes the charged particles stored in the conductor to create a current. The amount of current that's generated depends on the material and the resistance that's provided in the circuit. Okay. That's the end of the material in this chapter. So we can take any questions you have now. If people have any points that were confusing as they read through this chapter, we can talk about those now, or anything from today's slides. And I would propose that we just cancel lecture tomorrow. And we'll start chapter 28 as scheduled next week. And you can use the extra time tomorrow to start on homework, or contact me with any questions you have over the material. How does that sound? Is that okay with everybody? Anybody going to complain about a free Friday?
Well, that's awesome. Thanks.
All right. Are there any final questions over this chapter? Okay, so we will be jumping into chapter 28 next week, and I will send the announcement around probably tomorrow about reminders about everything that's coming due. Okay, anything else for today? If not, you're free to take off now, and we will touch base again either on Slack or in person next Wednesday. Okay, thanks everybody. Have a great day.